Now, before we wrap up the whole lecture, let me pose a little challenge for you. Right, so one of the most important concepts that we've learned today is that of the direction field of an ordinary differential equation. Right, so recall that the direction field of a differential equation y prime equals f of t y is just the vector field whose first component is 1 and second component is f of ty. And the direction field is a visual representation of a differential equation. All right, so we plot differential equations as direction fields. Now, there are several styles to do it. So notice that the style that we usually use throughout today's lecture is the first one. Right? So here we draw each arrow. Well, of course, we don't really draw it in scale, because if we draw it in scale, then usually it is too long. So we don't want them to overlap, right? But in this arrow, the x component of all these arrows is the same. It's not 1, but instead it's probably 0.1, but still is the same for all the arrows. So that's one possible style to do it. So another style here is that instead of drawing all the arrows so that the x component is the same, we draw them all of the same length. And the third style here is that we don't even draw them as arrows, so we just draw them as little intervals. For the purpose of visualizing the solutions of a differential equation, they are all equally good, right? So because what is the most important thing about these arrows is that every solution of a differential equation is a tangent to the direction field at each point. But of course, the fact whether it is tangent or not, it does not depend on the length of the arrow, and it does not depend on whether it is actually an arrow or an interval. So we can do it here, or we can do it here, so they're all tangent. The fact that they kind of all flow in the direction of the arrows, it can be visualized using all the three ways. So now, the challenge for you is to modify the existing MATLAB code. My MATLAB code is for this. This is the first of them, for the left one. How do you modify it to get this or to get this? So it's a bit of a challenge for you, and it is actually important because usually we are going to use this, and since it's the kind of the most convenient visualization to process. All right, and let me wrap up the lecture. So what we've learned today is that differential equations are, can be used to model a lot of real-life problems. So today we have seen the model of a fallen object, the model of a coffee that is cooling down, the model of the growth of population using differential equations. Then, usually if I just give you a differential equation, if it just comes out of nowhere, then usually it's impossible to solve it explicitly. Those little modeling examples that we saw today, they can be solved explicitly, but it's not always the case. And when one differential equation can be solved explicitly, usually a system, if it is a nonlinear system especially, then no chance that it can be solved explicitly. Well, but then, even if we cannot solve it explicitly, to determine asymptotic behavior of solutions, meaning when t approaches infinity, we can find equilibrium solutions, and then we can plot the direction field and look at how solutions approach, whether they approach equilibrium solutions or not. And hopefully you have learned the following skills: how to translate, well, at least some basic ideas about this: how to translate a real-world problem into a differential equation, how to plot a direction field of a first-order differential equation, how to find equilibrium solutions, and how to understand behavior of solutions